Okay, so if you recall from the page we had done prior, we were looking at three different approaches to finding the limits of a particular function. We looked at the notation for limits and we talked about what that meant. So one way is the numerical approach, which is the table, which is what is right here. One is graphical, which means you're drawing a graph. And then lastly, if needed, is the analytical approach, which means we're going to apply algebra. Okay. All right. So to kind of get a head start, I wanted you to already get this stuff written down. Now, this is what we call a piecewise graph. It just means there's more than one piece to it. And in this particular one, there's one, two pieces. You could have examples where there's three pieces. It would just mean that there are three bits of information that tells you how to graph this in its particular piece. For some reason, it seems like maybe it's we don't hit on it a whole lot prior, but sometimes it's a little bit harder for students to grasp a piecewise because we're so used to graphing just one equation. What does that graph look like? Okay, but this is what we call a piecewise. All right, it means we have two different bits of information. This is telling us that f at x equals 1. But it tells us that x cannot equal 2. Okay, what it's saying is x can be any number in the world except 2. So notice on my table, here's the 2. It can't be 2. Any other number that you choose, the output will always be 1. So if I were filling out this table, that would tell me that ones go here. Okay, so that's what that would look like in a table. Now, this is telling me that when x is 2, so f at 2, when you put 2 in here, it will always equal what? 0. So that's the ordered pair to 0. So we have two pieces. So f at 2 we know is equal to 0. I'm going to go ahead and graph that. 2, 0 would be right here. It is just a point on my graph. Okay, well, let's graph this piece. So we know the output will always be 1, but x cannot equal 2. So that tells me that f at x is always equal to 1. If I replaced f at x with y, I just want to graph the equation y equals 1. What kind of graph is that?
So for example, it would be 0, 1.
So notice it would be all of these. Where's -1, 1? That works. 0, 1. That works. 1, 1. That works. It can't be 2. So that's an open circle. 2.01 output is 1. 2, 3, 1. 3, 4, 5, 1. What kind of graph am I going to get if I connect all those ordered pairs?
Would it just be array?
What kind of line is this? Horizontal line. It's a horizontal line that crosses the y-axis at 1 because y is always 1. Now notice I have an open circle, and the reason of that is because their x coordinate cannot be 2. So this has two pieces. It has this horizontal line with an open circle, and then at x equals 2, we know its output is 1. So that's why if you were asked f at 2, when x equals 2, what is your output? 0. That's given right here. That is a different question than the limit. The limit is saying that as you approach 2 from the left and as you approach 2 from the right, what output is it approaching? What is this table approaching? What is this ordered pair of your open circle? Is it
0.
not 2, 1? So what is the output that it is approaching? 1. So the limit is 1. So f at 2 is this ordered pair. That ordered pair is 2, 0. That is why the answer to that question is 0. The limit that says, what is this graph doing as it approaches from the left and the right? It's approaching the output of 1. The limit is a different question than what is going on at that number. That's a whole new concept, I know. All right, so this is just reiterating some things that I've already talked about. Okay, now, yesterday, these examples, there was a limit. It was approaching the same number from the left to the right. Well, today we have to look at and consider limits that fail to exist or do not exist. Okay, so what would that look like in a table? All right, here's your equation right here. We want to know what is the graph doing as x approaches 0. So what is the limit as x approaches 0? So here's my 0. And we want to look at what's going on as the x value approaches 0 from the left. So if you were thinking of a number line, all of these numbers are to the left of 0, and it's continually getting closer and closer and closer to 0. What is this doing as the x coordinate approaches x from or 0 from the right? And as you can tell, these numbers are getting closer and closer and closer to the x value of 0. Okay, so if you were to look at this and start plugging these numbers in, you would have the absolute value of -1 is 1 divided by -1. So you'd have 1 over -1, which is just -1. And what you would find is every one of these numbers, when you did that, you're going to get -1. So from the left, as x is approaching 0, the output is also approaching -1. That's what's going on as we approach or do the limit to the left. Now, well, I don't want to do that yet. Okay, so now we want to look at what's going on as we approach 0 from the right. So I'm going to start with the numerical number 1. So the absolute value of 1 is 1 divided by 1 is 1. Not -1, but +1 now. And what you would find is as you would substitute those all in there, this would be 1, 1, 1. So the limit as x approaches 0 to the right, it is approaching what number? 1, right? Here's what the graph looks like. Here, here's your horizontal line where y equals -1. So this is the limit as x approaches 0 from the left, and it is approaching this output of -1, whereas from x values to the right of 0, it is approaching +1. So are they approaching the same number? No. So limits that fail to exist, behavior differs from the right and from the left. From the right, it's approaching positive 1. From the left, it's approaching negative 1. They are not approaching the same number. Therefore, that limit would be does not exist because they're approaching two different values. All right, so some questions that you might be asked. There is a difference between the question of f at 0. That is a different question than the limit as x approaches 0 for that function. These are two different questions. F at 0 was this ordered pair. So when x is 0, these are actually open circles. So we don't have an exact point at when x is 0. So this would be does not exist. Now, doesn't that make sense? What happens to the denominator if you put 0 in for x? You'd get a 0 in the denominator. That's an error. That does not exist. So this f at 0 does not exist. Okay, the limit, because they are approaching two different numbers, that answer is also does not exist. Now, I am going to go ahead and throw something else in here. Two additional questions we'll kind of see later. If this were worded, the limit as x approaches 0, and if I put a minus sign behind it, that means what is going on to the limit as x approaches 0 from the left. So as x approaches 0 from the left, what is it approaching? -1. So that answer would be -1. If I said the limit as x approaches 0 and I put a plus sign there, that means from the right. So it is approaching +1. And you can look at the graph and tell that as well. So they do have an answer if you specify from the left and from the right. Then if you just want to know the limit as x approaches 0, if these are not the same value, then it does not exist. Okay? All right. The limit as x approaches 0, 1 over x squared. So let me pull up Desmos, throw that in, and let's get a visual of what that looks like. All right, here's that graph right there. So I'm going to sketch that. Okay, so some questions you might be asked. What is f at 0? So do we have an ordered pair with an x coordinate of 0 to a point on the graph? Here's x equals 0. Is there anywhere I land on the graph? So what would my answer be? No, 0, 0 would be right here. Does not exist. Then if we get into limits, as x approaches 0, let me say from the left, what is that approaching? What number do we represent if it just keeps going up forever and positive what?
No, infinity.
Infinity. So this would be, it approaches infinity. It just goes on and on and on and on. What about the limit as x approaches 0 from the right?
You said positive infinity. Does it make a difference whether left or right if we do positive or negative infinity, or is infinity just
Negative infinity, you have to put the minus sign. Positive infinity, you do not. It's understood to be positive infinity. So like if this is positive infinity going up, you have to put negative infinity if you are representing negative numbers. But for positive, you don't have to. So what is this one from the right approaching?
Positive infinity.
Positive infinity as well. Now, in WebAssign, just read the directions because technically the limit does not exist. There's not a single number they're approaching, but it may ask you to enter infinity. So technically this does not exist because we don't land on one individual number. Now they are both approaching positive infinity, but there's not an individual number to represent that. So I can't remember exactly if WebAssign is going to want you to enter does not exist or positive infinity. So just be sure and pay attention. Okay. All right. So this is considered unbounded behavior because as x approaches 0 from either side, it increases without bound, which is what we represent as infinity. Okay. Now, what would happen, like, here's another example that still without bound. What if our graph gave us this? And so if I ask for the limit as x approaches 0 from the left, so in this case, I would be more specific and say what? Negative infinity. The limit as x approaches 0 from the right would be what? Positive infinity. So up here on this example, if they did want infinities as the answer, if you were asked the limit as x approaches 0 and it didn't say from the left or the right, are they both approaching positive infinity? Yes. So this would be positive infinity. Here, though, one is approaching negative infinity and one is approaching positive infinity. So if it asks as x approaches 0, meaning consider both sides, they are not approaching the same infinity. So your only answer is does not exist. Yep.
Infinities would only work. Which is 0 minus and plus.
If x equals,
Or like after that, what you say.
if you, typically you're going to see this if you have a rational equation. Is that kind of what you're talking about? Not always. I can't say in always.
Like if if x goes to 0 and it's like does not exist, but if it has like a plus or minus on the 0, that results in.
So in this case, if I did from the left and from the right, technically it is approaching positive infinity and negative infinity. Now, that means it doesn't exist, but WebAssign may want you to put in infinity. If you answered infinity on my quiz or my test, you're going to get credit for it. If it asks with no plus or minus behind it, it's wanting to know what's going on from both ways. And if they're not approaching the same thing, your only answer is does not exist. If they are both approaching positive infinity, then my answer would be positive infinity. Did that answer your question-ish? Okay. All right, moving on. All right, let's look at this equation right here. We have a rational equation, so we know we're going to have some restrictions on the value of x. So when you look at this, look in your denominator, what is that restriction? What number could you plug into x that if you subtract 2, you get 0?
Oh, 2.
2. So x cannot be 2. Because if we put x is equal to 2, then we get a denominator of 0. So what that tells me is f at 2. So when x is equal to 2, it would give me a denominator of 0. Therefore, at that point, it does not exist. All right, so now we're going to look at the limit. The limit is a different question. It wants to know the behavior of what's going on as it approaches left or right. So now we're looking at that same equation, but now x approaches 2. And so again, I would have your expectations that you could plug these numbers in. I'm going to give you the outputs to save some time. I will say, perk up, listen, listen, listen. It may affect you in a web assignment, a quiz, or a test. If this were a negative, by golly, if you have it squared, you better put negative 1.9 in parentheses. Because if you plug it in as this into your calculator, it's going to spit out a negative number. You have to put it in parentheses because that's technically positive. Okay, so be careful on that. All right, here are the outputs starting from the far left. 2.95, 2.975, 2.99. Okay, so the limit, and I'll write this down. So this right here would be, we're looking at what is the limit as x approaches 2 from the left. What does it appear that it is approaching? 3. So now we want to look at as x approaches 2 from the right. So that would be written the limit as x approaches 2 from the right. And we're going to see what that does. Okay, starting at 2.1, it would give you 3.05, 3.025, and then 3.01. So what does this appear to be approaching? 3 as well. So I'm going to put a 3 here because from the left and the right, it is approaching the same number. Now, this represents an ordered pair 2, 3. Here's where you need to be careful. Can the x value be 2? No. So at this point on the graph, it would be represented by an open circle. Okay? So this was the first way we looked at. Second was a graph, which you could graph in, you could plug this in and graph it into Desmos. Let me do that real quick. Okay, so I plugged this into Desmos and look what it gives me. What does it give me? What's that a graph of? It's not a trick question. What is it? It's a line. That's all I'm asking. It's a line. It's a blue line. Now, notice the 0.23. Well, because of the way this is being asked, 2,3, so I would come in here and that 0.23, I want to represent with an open circle. See how that's an open circle? So that is why f at 2 does not exist, because it's an open circle. But what is this approaching? It's approaching the ordered pair 2, 3. The output is 3, so it's approaching 3 from the left and from the right. Okay? All right, so then we get to the third, which is approach analytical or think algebra. So we have the limit as x approaches 2. Now notice I'm not doing left or right, I'm just doing 2. So that means I'm approaching from both sides. And then I want you to look at that equation. Look at your denominator. 2 times x minus 2. My numerator is a trinomial in descending order. So algebraically, I want to ask myself, is that factorable? Again, if you aren't solid in your factoring, I have some Algebra for STEM videos linked with Mrs. O'Neill, who's actually sitting in my room, and you can find her factoring lectures. Because I'm going to tell you, I'm not teaching you factoring. My expectations is that you can factor well, okay? So if that's a struggle for you, you're going to have to spend additional time outside of class. Trinomial, descending order, leading coefficient 1. So all I have to ask myself is, what are two numbers that multiply to give me -8 and add together to give me +2?
-2 and +4.
Now, how is that beneficial? That is called removing the hole. Because when we substitute a 2 in here, it creates that hole in the graph. We have removed that hole to allow us then, I am now left with the limit as x approaches 2, and I am left with x plus 4 over 2, or you could write it as 1/2 times x plus 4. If you wrote it as x plus 4 over 2, I'm fine with that. It doesn't matter. It means the same thing mathematically. You could distribute the 1/2 through, but technically we don't have to. We've removed that hole. So now what I'm going to do is what we call direct substitution. I'm going to directly substitute that in for the value. Okay, listen, when you do the direct substitution, your limit notation drops. So I would do 1/2 times 2 plus 4, 1/2 times 6, half of 6 is 3. This is my limit.
Where did you get the 1/2 from?
Those mean the same thing.
Oh,
So this is like x plus 4 over 1 times 1/2. I mean, that's a denominator, so you can just rewrite it that way. Yeah. If you wrote it like this, so if that makes more sense to you, instead of writing it this way, write it this way, you're going to put in 2 plus 4 is 6, 6 divided by 2 is 3, you're going to get the same answer. So if that makes more sense to you, do it that way. Okay? All right. Here we have a piecewise. This was kind of hard to enter into here. Okay, so all right, so let me do this. Here's one piece. Okay, so there's one piece of the graph. Now look, this is actually the exact same look at your numerator, x squared plus 2x minus 8. Whoops, sorry. X squared plus 2x minus 8, right? So that's the same numerator. What happens when you distribute this to 2x minus 4? So it just wrote it that way. Okay, so that's the exact same. We already saw that graph in Desmos. What did it graph? A line, right? But when it's written as a rational, what is the restriction on this? What was the restriction? X cannot be 2.
So you can't remove the whole.
No, we're not. This is a piecewise. We're not, you only remove the whole if it's asking you to find the limit. This is not asking you to find the limit yet. It's just giving you the information. So X cannot equal 2. So that is representative of this graph, and it has to have that hole there because X cannot be 2. So I'm going to graph that. Let me try to, I'm like, I need to put an actual, so over 2, up 1, 2, 3, that was a hole. And then this is something like this. Looks like that. Okay, so that is the graph of this. That's the first piece. Okay, the second piece is telling you when X is 2, what is its output? 5. That is giving you an ordered pair 2, 5. So over 2, up 1, 2, 3, 4, 5. That is what that would look like. Okay. So again, if this was the picture that you are given, you could be asked questions like, and I'm going to harp on this till we get used to the terminology, F at 2. Okay. It wants to know when X is equal to 2, what is its output? 5. That is a different question than the limit as X approaches 2. Here is that equation graphed. So as this approaches 2 from the left, the X coordinate 2 from the right, what is the output? This is the ordered pair 2, 3. What output are they both approaching? 3. Notice they have 2 completely different answers. That is probably one of the struggles my students have until they get used to this terminology and what a limit is as opposed. So just be careful of that. Okay. We've kind of already talked about this. This is our graph. Okay, so this point right here is -3. That's X is equal to -3. So if you were looking at a graph, and if I asked you, F at -3, I'm asking you, is there a graphed point when X is equal to -3? Hint, hint, both of these are open circles. I go over -3. Do I have a closed circle or a graph going up or down? Open circle, open circle. What does that mean this answer is? Does not exist. Then if we start having the conversation about limits, if I ask the limit as X approaches -3 from the left, be careful from the left. What is that point, open circle point? -3, -1, it appears. So what would this answer be? The limit as x approaches -3 from the right. What is this ordered pair? -3 up 1. So what would this answer be? 1. It's always the output. So when I look at this, if I'm asked for the limit as x approaches -3, if it does not specify the left or the right, then it wants to know what is it approaching from both sides. So ask yourself, do they approach the exact same number? No. If the answer is no, what is this answer? Does not exist.
So the limit is regarding to the y. I mean,
Always
that's
the
what
y coordinate. Always the y coordinate because your x coordinate is down here.
okay.
Okay. All right. This is a unique situation. This goes down here with this example. I don't know why I have so much space there. Okay. All right. So the limit as x approaches 0 for sine 1 over x. So we want to know as x approaches 0. All right, so technically here's what's going on, and then I'm going to give you the numbers, and then I'm going to show you in Desmos. Okay, this is 1 over x. So what that means is we would want to plug in sine of 1 over, and x I'm putting in -2 over 5 pi, which technically means then we're going to do 1 divided by, change that, you flip that. So technically what we're looking for is the sine of 5 pi over 2, and this is negative. And I don't have my unit circle with me. But if you looked on your unit circle, this would give you -1. Okay? So if we did that for each one, what you would find is this is 1, this is -1. Over here is 1, -1, 1. So notice how it's just going up and down, up and down, up and down. Let me show you what this looks like on a graph. You're not going to see this a lot. I just want you to get a visual of it. This is what we call oscillating behavior. Here's that graph. So as x approaches 0, it is just toggling back and forth, back and forth, back and forth, and it just creates so what do you think that limit would be? Does not exist. Okay? All right. So here's the situations that we have dealt with when we're looking for when the limit does not exist. One is when they approach 2 different numbers. They approached 2 different numbers, does not exist. One is when it increases or decreases without bound. So you're talking about positive infinity and negative infinity. We'll see these occur. This we just looked at. You won't necessarily see that much, if at all, but I just wanted you to at least take a look at that. Okay.
So oscillating was the one that shows in the graph, right?
Yeah. Yeah. Okay, so you do not have this. Oh man, and that is, I don't want to, I'm going to do it on the back. I don't want to mess up my paper. These are just some quick graphs that what you'll see on, there's 1, 2. I'm not going to do all of these. And then I want 1, 2, 1, 2. And then I'm going to do this. So this is 0.02. This is -2, -2. Okay. All right. So here are some possible questions you might be asked. F at -2. When x is -2, what is your output? Yeah, it's right here, this point. When x is -2, here's on the graph, its output is -2. This answer would be -2. What is the limit as x approaches -2? So now we're looking at, from the left, what is it approaching? The output of that ordered pair. What is it approaching from the right? Is it approaching the exact same number?
Yes.
Therefore, my limit is -2.
So that can also say negative infinity, or that would be a different.
This isn't infinity.
Oh, yeah.
If I was approaching something differently,
Yes.
like this goes on to infinity, but I'm not approaching the x value for that to occur.
And then the circle is complete. So
It is closed circle.
closed
Mhm.
circle.
As opposed to, I'll give you an example. Say we had, okay, I'm going to do the ordered pair -1, 2, but it's going to be an open circle. -1, 2, open circle, straight line. So this ordered pair is -1, 2. Then I'm going to do -1, 0 and do a closed circle. And it's going to look like this. So this point is -1, 0. All right. So what is f at -1?
So it'll be
Would it be 0?
It'd be 0. When x is -1, this is an open circle, so it's not that. I have a closed circle, so the y output is 0. So that's that ordered pair, -1, 0.
if it was just the open one, that it doesn't exist.
Well, this would have to be gone.
Yeah, that's what I asked.
If that was gone, your answer would be does not exist. Yeah. Then the limit as x approaches -1. So now we're asking a different question. Okay, so from the left, what is it approaching? 2. From the right, what is it approaching? Is it approaching the same number? Okay, so there is a difference in those two questions. So you have to be very careful of that. Okay, all right, we're going to stop there, which completes.
You know, way to ask the question.
Well, can you wait? Because I may get disconnected. All right, so 2.2 is complete. All right, so today is Monday. Okay, I'm going to go ahead and schedule it for Tuesday because I don't think it's one that will take a long time. If I look at that, I might change it, but I'm going to make it due tomorrow by midnight.
Today's Tuesday.
Today is Tuesday. Thank you. So let me reset that. Okay, so today's the 25th. You have 2.1 due tonight. I highly recommend that you also start 2.2 Um,